Okay, so let's start. I believe that the other people might join later if they want to. So today we are going to prove something which is very easy to state and which is a very beautiful theorem. And it's called the local Kronecker-Weber theorem. Local because there's also a global version. The global version works for Q. But the local version is over QP. So what does it say? It says that the maximal abelian extension of QP, so by definition, that is the extension of QP obtained as the compositum of all finite abelian extensions. That is by definition the maximal abelian extension. And the theorem is that this maximal abelian extension is obtained by just adjoining the roots of unity of various orders, all nth roots of unity for various n. So what we have seen earlier, that when you adjoin an nth root of unity to QP, you obtain, in fact, that's not special to QP. For any field whatsoever, if you adjoin an nth root of unity to that field, you obtain an abelian extension. The Kronecker-Weber theorem says that for QP, these are the only ones, or rather, every abelian extension is contained in some such extension obtained by adjoining an nth root of unity. So here is some notation. I have zeta n is an primitive nth root of 1. And then psi n is going to be zeta p to the n. So it's a primitive p to the nth root of unity, psi n. So instead of having to say every time that it's contained in some cyclotomic extension obtained by adjoining an nth root of unity, we have introduced this word which is cyclotomic. So the definition is that a finite abelian extension L of QP is called cyclotomic if it's contained in an extension obtained from QP by adjoining zeta infinity, which means zeta n for some n. If L is contained in QP zeta n for some n, then we say that L is a cyclotomic extension of QP. And obviously, if it is cyclotomic, then it is an abelian extension, because as I have just said, QP zeta p, zeta n in fact, over QP, or over any field whatsoever, when you adjoin a primitive nth root of unity, you get an abelian extension. So cyclotomic extensions are abelian. What we are going to prove is that every finite abelian extension is cyclotomic. So it's the converse, and the converse doesn't always hold. It holds only for some fields. It holds for fields such as QP. And for Q also, that's the global Kronecker-Weber theorem, which we are not going to prove, but actually which can be proved rather easily if you have done the local Kronecker-Weber theorem first. So this is the crux of the matter, even of the global theorem, that the local theorem holds. Okay, so this is what we have to prove. Every finite abelian extension of QP is cyclotomic in the sense of being contained in an extension obtained by adjoining a primitive nth root of unity for some n. Okay. So we will use some notation for every integer f. Kf is going to be the unramified extension of Qp of degree f. Now this Kf is cyclotomic in this sense, right? Cyclotomic has just been defined here. Kf is cyclotomic because Kf is obtained from Qp by adjoining zeta m, where m is p to the f minus 1. Of course, this f and this f are the same. Right? I mean, this is something which we must have proved already. That when you adjoin primitive mth root of unity for some m which is prime to p, you get an unramified extension, and you have computed the degree of that extension in terms of the m. So this should be fine, right? Now, I'll further use the notation Ln for k p to the n. So this is the unramified extension of Qp of degree p to the n. Kf is the unramified extension of degree Kf is the unramified extension of degree f, right? And Kln is the unramified extension of degree p to the n, right? Okay. Now here's a little exercise with this notation. So if you have L1 and L2, if you have two finite extensions of Qp, which are both cyclotomic, then so is the compositum L1, compositum L2. That's easy. That's because if you add, so that's easy because adding zeta n1 and zeta n2 is the same as adding zeta m, where m is, I don't know, what? Is it LCM or something? Yeah, maybe LCM of n1, n2, right? So if L1 is contained in QP, actually, okay, QP zeta n1 and L2 is contained in QP zeta n2, then L1, L2, this compositum is contained in QP zeta m, where m is this LCM of n1 and n2. That's right. Okay, so these are the preliminaries, mostly the notation and the definitions. Now let's come to the first proposition, which says that, okay, first consider the case p equal to 2 and take any integer which is strictly greater than 1. Then when I adjoin a primitive 2 to the nth root of unity, right? This is a primitive 2 to the nth root of 1. When I adjoin zeta n, psi n, sorry, not zeta n, psi n to Q2, that is the compositum of Q2 zeta 2, psi 2, excuse me, not zeta 2. Psi 2 actually is the same as minus square root of minus 1, because psi 2 is a primitive fourth root of unity. Primitive fourth root of 1, right? So when I adjoin psi n, that's the same as adjoining psi 2, and it's a compositum of this Q2 psi 2 and an extension m n minus 2, which is a totally ramified extension of the cyclic of degree 2 to the n minus 2. So in some sense, how do I put it? Yeah, so the diagram would be, you have Q2 here, you have Q2 psi 2 here, and you have m n minus 2 here. When you take the composite term, you get q2 psi n. So this is quadratic. I mean, this is of degree 2. This is of degree 2 to the n minus 2. And they are linearly disjoint, and this is the composite. This is the composite term of these two extensions. Now that's more or less obvious if you know the following facts. So what do you need to know? First of all, you need to know that when you adjoin psi n to Q2, you get an extension which is Galois and whose Galois group is isomorphic to this. Z mod 2 to the n star, the multiplicative group of Z mod 2 to the n Z. The next thing you need to know is that Q2 psi n is totally ramified over Q2. So first, from these two facts, you can't conclude, but you also know. Now you look at this is the Galois group of the large extension, right? And this psi 2 finally is what? It's psi n to the power n minus 2, perhaps, right? Yeah. So I'm looking at this projection here, this map here. This projection, it comes from this part of the diagram. I'm going to highlight it in yellow, maybe. So look at this extension and then this extension here. So this intermediate thing is the Galois group of the intermediate extension is a quotient of the whole Galois group. And that this is the quotient map. This map here is the quotient map, right? So, and what are the kernel is? The kernel, we know what the kernel is. In this case, it has to be, so you think of this Z mod 2 to the n as Z2 modulo 2 to the n Z2. We have seen that that's the same. And the kernel then would be U2 modulo UN, right? This is the kernel, where U2 is what? Those X in Z2 star, which are congruent to 1 modulo. This is UN, those X in Z2 star, which are congruent to 1 modulo 2 to the n, right? Yeah, here was the diagram that I was looking for. This is the extension that I'm looking at. So here's the Galois group of Q2 psi 2 over Q2, and here's the Galois group of Q2 psi n over Q2. And because this smaller thing is contained in the bigger one, you get this projection here, this projection, and this is the kernel of this projection. Now, what we know about this kernel is that it's cyclic of order 2 to the n minus 1. Not only that, this projection has a natural section. I mean, it just send minus 1 to minus 1. So in other words, what we are saying is that Z mod, maybe I should use a stronger color. What I'm saying is that Z mod 2 to the n Z star is really isomorphic to Z mod, it's isomorphic to U2 modulo UN times Z mod 4Z star. Okay, and so once you have this, you take, so once you have this kind of a splitting, the Galois group is written as a product, then of course you take the invariance under this factor here, And then that's going to be an extension of degree 2 to the n minus 2, which is cyclic because this group is cyclic, right? And which is totally ramified because it's contained in this totally ramified extension. Okay. So when n is equal to 3, right? Then what happens? Then this M1 has to be, of course, a quadratic extension, right? Because it's of degree 3 minus 1, which is 2. So it's a quadratic extension. And we know all the 7 quadratic extensions of Q2. So you have to identify which one is M1. So the hint is that M1 is contained in Q2 psi 3, for example, right? And it is fixed by this automorphism, which sends psi 3 to psi 3 inverse. So you just figure out which one it is, right? Which one M1 is. Okay. So now, what's the analog of this thing? When P is odd. If P is odd, you can allow n to be greater than 1 instead of requiring it to be greater than 2 as here, right? Okay. And then the claim is that QP psi n is the compositum of QP psi 1 and an extension mn minus 1, which is totally ramified cyclic of degree p to the n minus 1. Okay, it's totally ramified cyclic of degree p to the n minus 1. And the proof is exactly the same. You have QP psi n here, and psi 1 is q psi n to the power, what is it? P to the power n minus 1 or something? I would think so, yes. So this QP psi 1 is contained in QP psi n, and the Galois group here is Z mod PZ star. Let's just call it GP. And the Galois group here is Z mod P to the n Z star. Let's call it G P to the n. So you have, I think I should have written down, yeah, okay, so here it is. You have this projection, right, coming from this, the fact that this is the Galois group of the whole extension and this is a sub-extension. So you have this projection and it gets identified with the natural map from Z mod P to the n Z to Z mod P Z. It also comes from this here, right? And the kernel is U1 modulo UN. And we have seen that U1 modulo UN is cyclic of degree p to the n minus 1. Now, that is the exact sequence. And we have also seen that this exact sequence admits a unique section, omega, which is the Teichmüller section, right? The whole thing is totally ramified over QP of degree p to the, actually the degree is phi p to the n, right? The degree of QP psi n over QP, that is phi. The number of congruous classes modulo p to the n, which are prime to p, which are invertible in Z mod pz. Okay, so that's, this we know. This we know is cyclic of degree p to the n minus 1. And that's it. So you take a section, then you get a copy of this group GP inside GP to the n, and you take the invariance under that group. That's going to be something of, so that's going to be a totally ramified cyclic extension of degree p to the n minus 1. Because G to the Pn Gp modulo omega Gp, that can be now identified with this U1 modulo Un. Okay. So these are two very small lemmas. Basically, of course, we are using a lot of things which we have done earlier. So it says that these extensions Qp xi n, in the case of odd p, there's an extension of degree p to the n minus 1, and this extension of degree. The degree of this, of course, is p minus 1. And here the degree is p to the n minus 1. And similarly for Q2, of course, this is going to be of degree 2, and this is going to be of degree 2 to the n minus 2. So they have been written as composite terms of two extensions. Now here comes the proposition that if you take an abelian extension which is tame over QP, then it is cyclotomic. See, we have to prove that all abelian extensions are cyclotomic. We are proceeding sort of one by one. We are saying that if the extension is tame, then it is cyclotomic. So that's the proposition. Every tamely ramified abelian extension K of QP is cyclotomic. So let's abbreviate the ramification index by E and the residual degree by F. Then, so we sort of parametrized all tamely ramified extensions, abelian or not. We said that if we know the ramification index and the residual degree, then this extension is Kf. Kf is a degree, that notation is there, right? The degree F unramified extension of Qp is Kf. And to Kf, you adjoin a suitable, the eth root of a suitable uniformizer of Kf. This is what an arbitrary tamely ramified extension of Qp of ramification index E and residual degree F looks like. So let's write it this way. I mean, the way things. So this given extension K is abelian. So that forces a certain number of things. That forces that this P minus 1, E divides P minus 1. Because K over QP is abelian. So you have to go back to your notes about the parametrization of tamely ramified extensions. So, in fact, we will even So let's see. Yeah, so the important thing is I'm trying to think of a better way to say it. But anyway, let's just look at what is written here. So we know that E divides P minus 1. And now you write minus P as U times pi, where pi is what? Pi is a uniformizer of Kf, right? It's a uniformizer of Kf. Why can you write minus p as some unit times a uniformizer of kf? Because minus p is also a uniformizer of kf. And why is that? Because kf over qp is unramified. And minus p is, of course, a uniformizer of qp. And kf is unramified over qp. So it is a uniformizer of kf. So you write minus p as u times pi, pi being the uniformizer of kf, which appears here in defining k. Now, if I adjoin a p minus 1th root of u, I get an unramified extension k prime of qp. Adjoin this to kf, let's say, right? When you adjoin nth, if you adjoin, okay, so what is being used here? What is being used is that if L is a p field, n is some integer which is not divisible by p, and u is in OL star, then in this case, if you adjoin to L and nth root of u, this extension is unramified, right? This we must have recalled and used several times. So that's what is being used. This kf prime is obtained by adjoining p minus 1th root of u to kf. So it's an unramified extension of kf and hence of qp, because kf is unramified over qp. Okay, so you get this unramified extension, which is cyclotomic, right? I mean, every unramified extension is already known to be cyclotomic. So the point is that if you adjoin a p minus 1th root of some this uniformizer pi, then you get a cyclotomic extension. This is what we need to prove. But adjoining a p minus 1th root of omega of this pi is the same as adjoining a p minus 1th root of minus p, because minus p differs from omega by some unit, and we have adjoined a p minus 1th root of this unit, right? This is what we have already adjoined. So adjoining a p minus 1th root of minus p is the same as adjoining a p minus 1th root of pi. Okay, that's what is being used. But adjoining a p minus 1th root of minus p is the same as adjoining a pth root of unity. This is something that we had seen earlier, right? That if you adjoin a p minus 1th root of minus p, that is the same as adjoining a pth root of 1. This is something which we had seen earlier. So that shows that this tamely ramified abelian extension of QP is cyclotomic. So here's a simpler and more conceptual proof. What it says is that you just, if it's a tamely ramified abelian extension, it will be contained in the maximal tamely ramified abelian extension of QP, right? So it's enough to show that this maximal one is cyclotomic. Then, of course, this all sub-extensions of a cyclotomic extension are cyclotomic. That's obvious, right? Because in order to be cyclotomic, you just have to be contained in an extension obtained by adjoining a primitive nth root of unity for some n. Now, if you're contained in an extension, which is contained in an extension obtained by adjoining a primitive nth root of unity, then of course, the smaller extension is also cyclotomic. That's absolutely obvious. So you can show that the maximal abelian extension, which is tamely ramified over QP, is cyclotomic. And here is the idea. It's basically the same idea as this. So I'll not go into it again. Okay, so briefly, we know that this maximal abelian extension, which is tamely ramified over QP, is obtained by adjoining to the maximal unramified extension of okay, so here's some generality which is being said. That the generality is that if I have a P field F, no matter which P field, and Q is an or the number of elements in the residue field, then the maximal abelian tamely ramified extension of F is obtained from the maximal unramified extension of F by adjoining just a Q minus 1th root of any uniformizer of F. So when F is equal to QP, this Q is of course going to be equal to P. And then this FP is F infinity, the maximal unramified extension of QP is cyclotomic. I mean, that's obtained by adjoining the primitive nth roots of unity for every n which is prime to P. Okay, so that is cyclotomic. And then if you just adjoin primitive, not primitive, a P minus 1th root of minus P to get the maximal tamely ramified abelian extension. But adjoining a P minus 1th root of minus P is the same as adjoining zeta P. So basically you are just using this fact that this is adjoining this thing is the same as adjoining this zeta P. Okay, so you get that tamely ramified extensions, tamely ramified abelian extensions of QP are cyclotomic. Okay. So now I need to recall, and this is something which we had done. I'm not recalling it from any of your other courses. This is something which we had done in our own course. It's a purely algebraic result. And it talks about cyclic extensions of degree P of a field of characteristic P. So the field is going to be called F, right? F is a field which is of characteristic different from P. Did I say equal to P? Of course not. I want a prime number P which is different from the characteristic of my field. Then I can talk about a primitive Pth root of unity over that field. And K is the extension obtained by adjoining this zeta P to F. Of course, I get a Galois extension, and delta is I call the Galois group delta. And delta comes with this cyclotomic character, which gives the cyclotomic character. Where does it come from? Giving the action of delta on what I like to call K star, which is the multiplicative group of the field K, the P torsion. So this is the group of Pth roots of unity in K star. Not all of them are primitive, of course. One belongs to this group and it's not primitive. All the others are primitive because P is prime. So this is an FP space, or rather an FP line, FP space of dimension 1. So any group which acts on this FP line has to act through some character, and delta acts on it, and I'm calling omega the corresponding character, and it's called the cyclotomic character. These are things which we have already seen a certain number of times. Okay, now let's take a cyclic extension of F of degree P, call it E. I can take the compositum of E and K, which as an extension of K is cyclic of degree P, right? You have your F here, you have your K here, and you have your E here. This is of cyclic of degree P. This is cyclic. This is cyclic of degree. I don't know what the degree is, but I know that it dividing P minus 1, and then you take the compositum EK. So I get a cyclic extension of degree P of K, but K contains a primitive Pth root of unity, right? because of course K has been defined as F zeta P. So, and this is cyclic of degree P. Therefore, this Ek over K, let me use a different color. Okay, green should be okay. So this cyclic of degree P extension, because K contains zeta P, should correspond to an FP line delta, D, delta is the Galois group, D in K star modulo K star to the P. And of course, this Ek should be the extension obtained from K by adjoining the pth root of everything in D. So what is the upshot of this discussion on this page till now? What I've done is, maybe I should have summarized it. So the summary is that you have E over K, which gives you Ek over K, which gives you D in K star modulo K star to the power. Okay? And the proposition now says that this D is delta stable. What does delta stable mean? Delta, of course, acts on K star modulo K star to the power P. And this is an FP space, right? And this D is a line inside this. So the action of delta leaves that line invariant. That's what it means for D to be delta stable. And if it's delta stable, then delta acts on this D. And the proposition is saying that further, the action of delta on D is given through this cyclotomic character, which was explained here, right? So that is the proposition. I'm not going to prove it because we have proved it several times maybe in the past. And conversely, no, not so that was one direction. What was that direction? That direction was that E over F gave rise to D in K star modulo K star to the P. Omega. Omega here means that it's the subspace of this on which delta acts through omega. The omega eigenspace. The omega eigenspace. So E over F, cyclic of degree P, gives rise to an FP line in K star modulo K star to the P, omega, and now is the converse. Conversely, for every delta stable line in this, for every delta stable line in this, so the converse says that every delta stable line in this, K star modulo K star to the P, on which delta acts through omega, the cyclotomic character, there's a unique degree P cyclic extension E of F such that Ek is the same as K adjoin pth roots of everything in D. This is just the converse of what we did on this page here. Here on this page, we to a cyclic extension of degree P E over F, we adjoin an FP line D in K star modulo K star to the P omega. Conversely, given any D, an FP line in K star modulo K star to the P omega, we are saying that there's a unique cyclic extension of degree P over F, which gives rise to this D by the process described earlier. Okay, so here's the summary. The summary says that on the one hand, I have the set of degree P cyclic extensions of F, which is sort of unknown. Given a field F, I don't know what the degree P cyclic extensions of that field are in general. One doesn't know that. But given given this k, you may think of computing k star modulo k star to the p and the omega eigenspace. And of course, then lines in this will, if there's a natural bijection, then given by this, then you have sort of understood this set. You have put it in bijection with a known set. So this is a slight generalization. So instead of just looking at cyclic of degree p, I look at any abelian extension of f of exponent dividing p. So cyclic of degree p corresponds to the Galois group being this. Now I'm allowing the Galois group to be z mod pz to the n. So, okay, I mean, maybe one should, yeah, just n or even infinite is allowed. So let me, if you just want it to be finite, then subspaces of the FP spaces. So then you have to put finite dimensional here. So yeah, okay, let's just n. But this n is not fixed, for varying n. So what are we looking at now? We are looking at finite abelian extensions of f of exponent dividing, what is p? Yeah. How can things divide p, which is a prime number? They can divide p by being equal to 1 or equal to p, right? So the exponent could be 1, which means that the group could be trivial. So I'm not leaving out the extension f over f. I mean, that extension is also allowed, right? In that case, the finite dimensional subspace corresponding to it will be the origin. I mean, this is a vector space over Fp. The origin is a subspace of dimension 0. But in general, you are looking at k star modulo k star to the power p. You are looking at the omega eigenspace. So the omega eigenspace for the action of delta on this, right? And then you are looking at finite dimensional subspaces of this Fp space. So this is sort of computable. And this is unknown. And Kummer theory parameterizes this unknown set in terms of this computable set. When does an abelian extension, so this is an abelian, okay, let's say finite abelian extension of f of exponent p, and this is a subspace of this, of the omega eigenspace, right? When do they correspond to each other? Precisely when you take the compositum Ek, it's obtained as an extension of K by adjoining the pth roots of everything in K star, whose image modulo K star to the power P is in V. The dimension, the degree of E over F will be equal to the dimension of F of V as a vector space over Fp. And of course, E1 is going to be contained in E2 if and only if V1 is contained in V2. So this is called Kummer theory, and I'm not going to insist too much because we have seen this before. Now, I'm sorry that I used a pen, maybe which is not so visible on some of your screens. So I'll sort of, let me see if I highlight it with some red or something. No, then that's terrible. Okay, so no. Let's see. I'll read it out, doesn't matter. So I'm looking at now, the next thing is about cyclic extensions of degree P are cyclotomic. That is, we are looking at the case P different from 2, and we are going to show that cyclic extensions of degree P are cyclotomic. I mean, of course, degree P, I mean, all this is, we're talking about extensions of QP, right? The whole thing today is about extensions of QP. So this is the proposition, every degree P cyclic extension of QP, P different from 2, but that is only for this proposition. Then we will remove P equal to 2. So P equal to 2 will be treated next. That's right. Yeah. So every degree P cyclic extension of QP is cyclotomic. That's the assertion. Now, recall our notation. L1, what did it stand for? It stood for the degree P ununified extension of QP. And M1, what did it stand for? It stood for the totally ramified cyclic degree P extension of QP contained in QP psi 2. And psi 2 was the same as zeta P squared. So this M1 is, of course, cyclotomic because it's contained in this QP psi 2. Psi 2 is a primitive P to the P squared root of unity. Okay, so that's when we are continuing the proof. So it's enough to prove that if E is cyclic of degree P, then E is contained in the compositum of stopped working. Oh, that's not good. So E is contained in the compositum of L1 and M1. It's enough to prove that because L1 is cyclotomic, M1 is cyclotomic. Therefore, their compositum is cyclotomic. And if E is contained in the compositum, then of course this this E is also going to be cyclotomic. Let me wait for 2 minutes to charge my pencil, and you can ask any questions till then.
Sir, kindly unmute yourselves.
Okay, sorry. Yeah. So if you are told to produce a ramified degree P cyclic extension of QP, it's not obvious. So this is going to be a consequence of this inclusion. And I had said that the Galois group of L1, M1 over QP is this Z mod P cross Z mod P. And therefore there are P plus 1 quotients of order P. And therefore there are P plus 1 cyclic extensions of degree P over QP. There'll be a corollary once we prove this inclusion. Okay, so now how do we prove the inclusion? That every cyclic extension of degree P over QP is contained in L1, M1. That's what we want to prove. Now we recall all these details about cyclic extensions of degree P of a field which of characteristic different from P. QP, of course, the characteristic is 0 and not P. So if K is QP zeta P, then these degree P cyclic extensions of QP correspond to lines in the omega eigenspace, as we have just seen, right? Omega eigenspace, K star modulo K star to the P omega. We already know two such cyclic extensions. We know L1 and M1. They have to correspond to some lines here. And you can ask which lines in this space do these two extensions correspond to. Now, at some point, we had proved that the unramified extension corresponds to this line. The unramified degree P extension corresponds to this line. We had proved it for every P field of characteristics 0. And what is also clear that this M1 corresponds to the image of K star P, the P torsion, the group of pth roots of unity in K star. That is an image in K star modulo K star to the power P. And we had seen that delta acts on this image through omega. So this image is in the omega eigenspace. So now we have found the two lines in K star modulo K star to the P omega, which correspond to the extensions L1 and M1. And the lines are UP bar and K star P bar. The claim is that the whole eigenspace is generated by these two lines. Okay? Now, why is that true? That is true because we had analyzed the action of delta on K star modulo K star to the power P. When proving Serre's mass formula, we had described precisely which characters occur in which subquotients of K star modulo K star to the power P. So if you go back to that analysis, then you will see that the omega eigenspace not only contains these two lines, but is generated by these two lines. In other words, there's nothing else. So any line in that omega eigenspace is, if I take the corresponding cyclic degree P extension of QP, then it's contained in L1, M1, in the compositum L1 and M1 corresponding to these two lines. So that proves this fact that E is contained in L1, M1. Another corollary is that if I take the maximal abelian extension of QP of exponent dividing P, which is to say if I take this compositum of all cyclic extensions of QP of degree P, then I get just L1, M1. So this is of degree P squared over QP, of course. Okay, so now we are continuing to assume that P is different from 2. And it says that every finite abelian P extension, P extension is something whose degree is a power of P. I don't specify which power, but it could be of degree P or P squared or P cubed, but it has to be a finite abelian extension, call it A. Then the claim is, the proposition says that the Galois group of A over QP can be generated by 2 elements. I'm not saying that you always need at least 2 elements. I'm saying 2 elements suffice. So sometimes 1 element might suffice. Of course, it will suffice precisely when the extension is cyclic. But when the extension is not cyclic, 2 elements will suffice. That's the content of this proposition. And here's the proof. So the proof says that if you take any abelian commutative P group, the minimal number of generators of this group is equal to the dimension over Fp of G modulo G to the power P. The G to the power P is, of course, the image of the multiplication raising to the power P map. It's G to the power P is equal to the image of the map which sends x to x to the power P, x in G. Okay, so it's a subgroup, right? Because this map is a homomorphism when G is commutative, right? Okay. So this is a fact about group theory, which I assume that either you know or you can prove. A finite abelian P group can be generated by it can be generated by as many elements as the dimension of the quotient G modulo G to the P over the field Fp. So, but I need to prove that, yeah, so I'm sorry to have used this color, which is not visible even to me. So I don't know whether it's visible to you. But, okay, so basically, the reason is here. Did I say? Yeah. Okay. Yeah, so let me explain it here. I'm sorry that I didn't leave out any space. So here's the basic reason. So you take the Galois group of A over QP, right? And let's look at this G modulo G to the P. This is what? This is abelian of exponent P. So hence a quotient of Z mod PZ2. Why? Because every abelian extension of exponent P is contained in the extension L1M1. That's what we have proved here, right? It's contained in the extension L1M1. And the Galois group of the extension L1M1 is this Z mod PZ square, 2 copies. So any quotient will be generated by 2 elements, and therefore the dimension of this as a vector space over Fp is at most 2, and therefore the G can be generated by at most 2 elements because of this group theory lemma. So that was the argument. So now we are looking at P equal to 2. Till now we had assumed P odd for many of the statements. For example, to show that every cyclic extension of degree p is cyclotomic. Now let's do it for p equal to 2. So every quadratic extension E of Q2 is cyclotomic. In fact, E is going to be contained in L1, M1, Psi2. Psi2 is -1, so that's cyclotomic. L1 we know is cyclotomic, M1 is cyclotomic. So the composition of all three is also cyclotomic. So clearly, I mean, if it's a quadratic extension, then it's contained in Q2. And if you join the square root of everything in Q2 star, that contains all quadratic extensions. But what is Q2 star modulo Q2 star squares? That it has a basis, F2 basis consisting of -3 bar, -1 bar, and 2 bar. If you join a square root of -3, you get the ununified extension L1. If you join a square root of -1, you get this square root of -1 is Psi2. And if you join square root of 2, you get M1. This needs to be checked. I mean, it was an exercise earlier, and so when you take the composition, you get this thing. Now, each of these three is cyclotomic, so the composition is cyclotomic, and hence every quadratic extension of Q2 is cyclotomic because it's contained in this. Okay. Now, the same thing for p equal to 2, right? That if I have an abelian extension, abelian 2 extension of Q2, then the group can be generated by 3 elements. This was 2 for odd times p. Here I need 3 elements at least. Okay, so it suffices to prove that if I have so A over QP, Q2 rather, right? Q2, you have the group G.
Sir, I can see your screen. Whether others are.
You cannot see the screen?
To see, I don't know.
You cannot see the screen?
No, sir. No,
Sorry?
I don't know about the others. I can see your screen. I can't see your screen.
You can or you cannot?
I cannot.
That's, oh yeah, it's frozen. Even in my, oh, okay, so it's not moving?
No, it's not.
Yeah. Okay, yeah, right. So let me see if I can, let me just stop sharing and then reshare to see if it works. So I stop sharing. No, it doesn't work. So maybe somehow it has lost connection. This iPad, yeah. So let me see if I can share. Yeah, it had lost connection. So join which one? Okay, I'll just join again. Let me see. Okay, now you can see it, right?
Yes, it's fine.
Yeah, okay, good. So let's continue. So I was saying that you have this abelian extension A of Q2, in G is the Galois group. It's an abelian 2 extension, so this is a 2 group. And I have to show that it can be generated by 3 elements at most. And right, so as before, I have to show that the dimension of G over F2 of G modulo G squared is at most 3. Okay, so yeah, you have this G squared over Q2 and you have this extension, right? But this, yes, this extension here is the Galois group here, the Galois group of this AG2 over Q2, that's equal to G modulo G squared. So this is a 2 group killed by 2. It's the same as saying, I mean, it's of exponent 2. And if it's of exponent 2, it has to be contained in this thing, right? So this AG2 is contained in Q2 zeta 24. I should have said here that yeah, this is also equal to Q2 zeta 24. The maximal abelian extension of Q2 of exponent 2 is obtained by adjoining a primitive 24th root of unity. Okay, so yeah. So if it's contained in this, then the Galois group here has to be a quotient to the Galois group here. But the Galois group here is generated by 3 elements. Because this is, here, the Galois group is just Z mod 2Z cross Z mod 2Z cross Z mod 2Z. Okay, so this Galois group here is generated by 2 elements. So this one is generated by 2 elements. So this whole thing is generated by 2 elements. There it is. Okay. Here is an exercise which is perhaps not visible. So it says that if you take f equal to q2, to which I adjoin minus root of minus 1, which we have been calling psi2, then none of the quadratic extensions of this f is cyclic over q2. So you have q2 f, and I take a quadratic extension, let's call it e. So this is of degree 2, this is of degree 2. Now this is of degree 4. This is Galois, but this is never Galois. That is what is being, no, that's not a good idea. No, it's not. I'm not saying it's never Galois. Sorry. What I'm saying is it's never cyclic. It can be Galois, of course. I mean, you have the Galois group could be Z mod 2 cross Z mod 2, but it cannot be Z mod 4. That is an exercise. And how does one prove such a thing? You just need to enumerate all the quadratic extensions of Q2 root minus 1 and just check that none of them is cyclic over Q2. But I mean, this is a very, very special case of some very general algebraic facts. Ultimately, it happens because this Hilbert symbol minus 1 at 2 is minus 1. We talked about Hilbert symbols. And in general, if you are given a field f, you can ask, when is a cyclic quadratic extension of f embeddable in a cyclic quartic extension of f? And you could do more. You can choose a prime L, not just a prime 2, but any prime L, and ask, when can a cyclic degree L extension of f be embedded in a cyclic degree L squared extension of f? So these algebraic questions have answers, and we are not going to discuss it here. But what we need is this fact, which can be verified directly. And so let's get going, because I'm running out of time. So here is the main statement, right? Every finite abelian, oh, it's not main yet because I'm saying P extension. So every finite abelian P extension K of QP is cyclotomic. Let's see why. It's a Galois extension, so let G be the Galois group and let T be the exponent of the group G. Exponent of the group G. Okay. T or P to the T. It's not T, it's P to the T. I mean, the Galois group, yeah. It's a P group. So the extension, the exponent is a power of P, and maybe it's, yeah. P to the T is the exponent of the group G. Now, in order to show that K is cyclotomic, I can replace K by a bigger extension, right? It's enough to show that K LT MT, which contains K, is cyclotomic. Right? Remember that LT is the unidentified extension of QP of degree P to the T, and MT is the extension of degree P to the T contained in QP psi psi T plus 1. That is when, am I assuming that P is different from 2 or something? Yeah. So I'm assuming here P is different from 2. That's right. Yeah. Oh, well. I mean, I'm assuming P is different from 2 from here onwards. So here it was all right. I mean, in the statement, I mean, it's true for P equal to 2 as well, but you need to distinguish the cases by proving it. So, I mean, by replacing K by this K LT MT, you can assume that LT MT is contained in K, and it remains a Galois extension of QP, and the Galois group continues to have exponent P to the T. Now, we have seen that G can be generated by 2 elements. Now, this is what we have already proved. What else do we know about G? It has exponent P to the T. And it has this quotient, the Galois group of LTMT over QP, which is of type P to the T, P to the T. Right? Here's the picture. Here's the picture. First, we assume that K contains this extension. We can do that because we want to prove that K is cyclotomic, and if K adjoined LTMT is cyclotomic, then of course K is going to be a cyclotomic. When we adjoin LTMT, I mean, we continue to get a Galois extension, and the Galois group continues to have the same exponent P to the T. And so then there is this intermediate extension, which is, as I said, what is LT? The Galois group of LT over QP is Z mod P to the T Z, and the Galois group of MT over QP is also Z mod P to the T, right? So this is of type P to the T, P to the T, and it's contained in this extension. So G has a quotient of type P to the T, P to the T. Okay. Now, if you have a commutative group G, which has these 3 properties, it's generated by 2 elements, it has exponent P to the T, and it has a quotient which is of type P to the T, P to the T. Then, of course, G itself has to be of type P to the T, P to the T. The structure theorem of commutative groups, you just think about it, and you immediately get this conclusion. Now, if G itself is of this type, then K will have to be equal to LT, MT, and therefore K is cyclotomic because LT, MT is cyclotomic, right? That we have seen several times. And then we come to the case P equal to 2. This was P odd. Here, t, it's not t, it's p to the t is the exponent. It's in fact not even 2, it's 2 to the t is the exponent of g. Yeah? It's a 2 group, g is a 2 group. So the exponent, I'm calling it 2 to the t. So we, as before, we can suppose that this K contains LTMT. This is LT cyclic of degree 2 of order 2 to the t, and MT is also cyclic of degree 2 to the t. It's contained in this cyclotomic extension. Anyway, so yeah, and of course, we may also assume that psi2 is also contained in K, right? It should be psi2 here. So now you have this group, Galois group of K over Q, Q2, which continues to have exponent, where is it? Yeah, it has, so G has exponent 2 to the t. It is generated by 3 elements, which is what we had proved earlier. It has a quotient, which is of type 2 to the t, 2 to the t, 2. Where does this come from? This is L1, M1, Q2, psi 2. These are all cyclic extensions of Q2 of degree 2 to the t, 2 to the t, 2. Right, so that's, and they are linearly disjoint, so that is an extension of type 2 to the t, 2 to the t, 2. And what we know is that it does not have a cyclic quotient, G mod H, of order 4, which contains psi2. Because, why is that? Why does it not have it? Because there is, we said, you take Q2, you look at Q2 psi2, and some quadratic extension E, this can never be cyclic. This can never be cyclic. So it doesn't have a quotient of order 4. This forces G to be of type 2 to the t, 2 to the t, 2. And therefore it forces K to be LT, MT, psi 2, and which is cyclotomic. Therefore, K is cyclotomic. That completes the proof in the case P equal to 2. Fine. So now we are almost done. Now let's come to the general statement, which is that every finite abelian extension K of QP is cyclotomic. Now G is an abelian group, right? This is commutative, finite commutative. So I can always write it as P cross P prime, where capital P is a little p group and capital P prime is a little p prime group, which means that it's of order prime to P. Where G is the Galois group, of course. Okay. Then what is the picture I get? I can take the invariance under P prime and the invariance under P. The invariance under P prime are going to be an extension whose Galois group is this capital P. And the invariance under P is going to be a Galois extension of QP whose Galois group is P prime. So, and K is going to be the compositum of these two things, because G is equal to P cross P prime, right? So it's enough to prove that this and this are cyclotomic. Now K to the fixed field under P prime is cyclotomic because it's an abelian P extension. It's a P extension. That's what, and for P extensions, we have already proved that P extensions are cyclotomic. What about the other thing? Why is K to the power P? It's not K to the power P. It's a fixed field of this field, of this group P. Why is it cyclotomic? It's cyclotomic because it's a tame abelian extension of QP, right? It's tame because the degree is prime to P. So it may be ramified, unramified, whatever. If it's ramified, it's tamely ramified. It's not wildly ramified. And for tamely ramified extensions, we have already proved that they are cyclotomic. And therefore, the compositum is cyclotomic. Okay, so this is what this finishes my lecture today. And I just wanted to emphasize that the proof is really, really nice in the sense that it uses, there's no subterfuge, there's no ad hoc things. It uses things which are kind of, it uses the structure of the underlying things. And it uses many of the things which we had covered earlier, like this omega eigenspace and how lines in this omega eigenspace correspond to cyclic extensions and so on, right? So I'll stop here and see if there are any questions. Yeah? So if there are no questions, I'll stop the lecture here. Right, and see you on Monday. Oh, before that, we have a tutorial on Friday. Yeah. Okay.